In this lesson, I will be explaining how to shift the index for a sequence. So to start out, let's look at a couple sequences and just write out a few terms. And you'll see something interesting happen, hopefully. In this first case, we're starting with n equals 0 and plugging that in. So I'll indicate which n value we're using, and then I'm using an just to represent this sequence, and we will have the first term. Well, we can call it the first term, but we're using n equals 0. And so some might call this the 0th term. Anyhow, it's a with a subscript of 0, and we can get that by just plugging in our 0. So 0 squared plus the cube root of 4. And we don't need to simplify. In fact, I'll leave it unsimplified so you can see a pattern. If we plug in 1, then we're looking at the term a1, and we have 1 squared plus the cube root of 1 plus 4, so that's just the cube root of 5. Let's write out a couple more terms here. It's asking for 4 terms, so we have 0, 1, 2, and 3 in our case. So a2 is going to be 2 squared plus the cube root of 2 plus 4 there, so that's cube root of 6. And then finally, a3 is equal to 3 squared plus the cube root of 7. Okay, so we finished off writing out the first 4 terms of this sequence. Check out this other sequence to the right of it. This starts at n equals 3 and goes to infinity, but at a glance, you might notice it's of a very similar form to this sequence. Let's see what happens here, starting with 3. And we are going to do 4 terms, so we'll go 3, 4, 5, and 6. And plug it in. So 3 minus 3 squared, that's 0 squared, plus, oh, I should actually indicate this is a different sequence, so I'm going to give it a different name. I'll call this Bn. So B with a subscript of 3, that will equal, and then we'll have whatever we get when we plug in 3. So 0 squared plus the cube root of 3 plus 1 in the radical, so that's 4. 0 squared plus the cube root of 4. That should look very familiar. And when we plug in 4, see what happens. Well, 4 minus 3 is 1, so 1 squared plus the cube root of, under the radical, we have 4 plus 1, so that's 5. Yes, we're getting the same terms as we had in the other sequence, the one that I called an. The first 4 terms are exactly the same. So if we look at B5, just to double check, 5 minus 3 is 2, so sure enough, 2 squared, plus now the cube root of 6, and sure enough, B6 will equal 3 squared plus the cube root of 7. So the takeaway here is that these do represent the same sequence, but you can see that the starting index value is different. N equals 0 versus n equals 3. So naturally, if they do represent the same sequence, we wouldn't expect there to be the same formula. But nonetheless, we should see the first term matching up, second term matches up, etc. And that's how we can really identify they are the same sequence. So there is a way to actually rewrite the sequence with a different index. Suppose you were given this n squared plus the cube root of n plus 4 formula starting at n equals 0, and you were asked to rewrite this perhaps starting at n equals 1 or n equals 2 or some other integer. This process is called shifting the index. And it's explained in this paragraph here. The choice of the starting index value is arbitrary. As you can see, for a sequence, it's not like we have to start with 0 or 3 or anything in particular. So it's definitely possible to rewrite the same sequence using whatever starting integer you want, shifting the index, in other words. So to capture this idea, let m and h represent integers. If we have some sequence an that starts at n equals m, like to use a concrete example, it could be n equals 0. And then we want to rewrite it in a way where we're starting with a different n value. So let me type this in here. For example, n equals 0 could be the starting value. And then this is our capital M is 0. And for example, h could equal 3. And that's what we saw here, that to go from n equals 0 to n equals 3, we have to rewrite the formula. So each n value, or each n in the expression, I should say, we have to subtract 3 from it, or we have to subtract h from it in general. We'll rewrite a sub n as a sub n minus h. So to show you one example here, using the same idea, but starting with a different value, let's say we want to actually start with n equals 2. That's 2 more than 0, so we have to subtract 2 from each n in the expression. We'd have n minus 2 squared plus the cube root of n minus 2 plus 4. So when you combine like terms, that's actually n plus 2. And you should see with this sequence that I just wrote starting at 2 and going to infinity, you will get the same terms as these other ones. So that's the idea of shifting the index. Try out example 4. Rewrite this sequence to have a starting index value of 5. It's cosine of 2n plus 1 over n plus 8. Hopefully you had time to work on example 4. If you haven't yet, go ahead and pause the video and try it out yourself. We're asked to rewrite the sequence to have a starting index value of 5. I noted here that the given sequence starts at 1. So if you're looking above at this formula, how to shift the index, the big M is our starting index that's given. In our case, big M is 1. We'd like it to start at 5. So we're aiming for a sequence that will begin with n equals 5. So naturally, the question arises, well, what's the little h? If big M is 1, and this is equal to 1 plus h in our case, we can see that h is 4. In other words, the little h is however much you need to add to the m value to get to the index you need. So that fact that h equals 4 now tells us how to shift the expression. Anytime we see n, we need to replace that with n minus 4. So we'll have cosine of not exactly 2n minus 4, because we're just replacing the n with an n minus 4. So it'll be like this, 2 times the quantity of, in parentheses, n minus 4. And later on, we will distribute this 2, and we'll get 2n minus 8, in fact, on the inside. But we'll do that later. Then for the next term, it was originally 1 over n plus 8. Remember, each n we are replacing with n minus 4. So we'll have n minus 4 and then the plus 8. We can simplify that later. Let's go ahead and do that simplification. So we have the cosine of 2n minus 8. And then it's that plus 1 over, simplifying this denominator, n plus 4. Yep, so that's our expression, and it goes from n equals 5 to infinity. And that's it. You could, if you'd like, check to make sure it works. When you plug in 5, for example, you should get the same output here as you would get plugging in a 1 from the given expression. In fact, just looking at the 1 over n plus 8 part of it, I can see that originally if you plug in 1, you should get 1/9 for that component. And here, sure enough, if we plug in n equals 5, we do get 1/9 for that component. That finishes example 4.